explore Mars because we're looking for signs of life. Life anywhere else in the universe would be a fantastic discovery. There are other locations in the solar system where there could potentially either have been or even be life now, but Mars is the closest place where there could possibly have been life 3.8 billion years ago. The Mars that we have now is very different. At that time, there was rampant volcanism, there was a magnetic field, there was a thick atmosphere, there was water on the surface. So we think that life could have existed on the surface of Mars at that time. Because of the way that the planets line up, that gives us the possibility of sending orbiters or landers every 2 years. Every time we have a new mission, we find out new things, and so you're able to enhance really the tree of knowledge. Missions up to now have been looking for signs of water and for signs of habitability. The missions in the next few years are going to be looking at, was there life there? Could there even be life there now? By drilling underneath the surface, which is ExoMars' unique feature, that is going to give us the best possibility for getting below the really inhospitable environment which there is on the surface of Mars, a very oxidizing environment, there's a higher radiation environment, there's no magnetic field to speak of, and so that means that it's inhospitable now.
The search for life on Mars is an incredibly challenging endeavour. Despite all the missions that we've had to Mars over the past kind of 10 to 20 years, we still don't know an awful lot about the actual chemical environments that might have existed. To understand what type of life may have actually been able to live in these environments is actually very challenging. So to tackle this, we try and look at really extreme environments on Earth. For example, some of the brines that Mark looks at, to try and understand exactly kind of what types of life might have been able to survive there.
You use data from spacecraft, and as Claire was saying, these missions are very technologically challenging. So before we design a mission, before we send it out there, we have to know where we want to send it to be able to bring the risk down and be able to bring the potential for a scientific return up. So to do that, we create some of these types of environments here in the lab and try and piece together what about them makes them potentially a habitat or not a habitat for life. Here's an example of a simulated Martian brine. The green colour comes from a high level of dissolved iron. We look at microbes that live in high salt environments. We pull out microbes from there and we try and understand how they survive in these types of environments to give us a better idea of where to target with a spacecraft.
Yeah, and this is really important because Mars is huge, right? You have this entire geological surface to try and explore with a handful of missions, and ExoMars is just one rover going to one particular locality on Mars. So in order to target it to the right areas, you want to really be able to identify what particular minerals we really want to be trying to focus on.
So this is one of the microbiology labs. It's like a giant zoo of different microbes from extreme environments. By looking at how those microbes survive in extremes, we can start to map the extremities to which life can survive. Now we're entering the anaerobic laboratory, and what we do here is we study microbes under conditions that have no oxygen. Deep underground, there is no oxygen, and microbes that live there live in the absence of oxygen, as would anything living, for example, on another planet like Mars. So we're going into the lab now where we have a simulated Mars chamber that allows us to recreate conditions, liquid conditions on the surface of ancient or present-day Mars. We have these sample pots here where we can look at the interactions between liquid and solids like rocks, and we can flow liquid through and we can look at the gases being produced. This is part of the effort to recreate environments on the Earth. It's very difficult to send missions to Mars, so the cheapest way to look at ancient Martian environments is to recreate them on the surface of the Earth. And that's precisely what we're doing here.
So what we're looking at here are actually some organisms that are quite happy growing under a certain set of characteristics that are common on Mars, or at least were common in a certain type of environment on Mars. They might look small, but these guys are living in a very extreme environment, very, very low pH, high levels of iron, and very salty as well. So it's the kind of environment that would have existed for actually quite a long period of time throughout Mars's surface history.
Astrobiology is a very old field in the sense that people have been asking, is the Earth the only planet with life for a long time? I think what's changed in the last 20 years is it's become a much more empirical field in the sense we have missions going to other planetary bodies. We know a lot more about the limits of life on Earth, primarily because of advances in microbiology. Planetary missions in general are very interdisciplinary. You need chemists to understand the past chemical environment, you need physicists to understand the conditions that may have existed in the past and how they were shaped by the physical environment, and you need biologists to be able to take that data and assess whether it matches up to habitability. The primary objective of ExoMars is to study the habitability of Mars. It will also look at possible biosignatures of life. What we do know is that there are environments that have all the requirements for life, the right elements, possible energy sources, and liquid water. And so the obvious step is to go and see whether those environments ever supported life.
Just by looking around this landscape, I hope you can get a real feel for why it is that planetary scientists and astrobiologists like myself really want to come to the Atacama to do our field work. This is a barren, desolate landscape, and you could really convince yourself that you were on Mars, that you were walking across the Martian landscape. It looks just like this. But in particular, the Atacama Desert is useful for astrobiology and understanding about the possibility of microbial life on Mars, because this desert is one of the oldest and driest deserts anywhere on the Earth, and therefore, in that respect, reproduces the conditions that exist on Mars, where it's also exceedingly dry. Any life that can survive here in the Atacama, and that's what this research trip is all about finding these extremophiles, those very hardy bacterial cells in the soil or living inside the rocks to protect themselves here in the Atacama, to try to understand what life on Mars would also be like. What kind of survival tricks would it have to employ to survive the very dry conditions on Mars?
This mission distinguishes itself by being the first to drill really well underneath the surface of Mars, up to 2 meters underneath the surface. So with the PanCam instrument, we're seeing the broad scene, the rocks on Mars, looking for outcrops and looking for potential interesting sites to drill. So then the drill goes under the surface, gets the rocks from under the surface, and the Raman is one of the instruments which is looking at the rocks under the surface. So the powerful combination which we have is the visual and near-infrared imagery from PanCam, and then the spectroscopy from the Raman team. So it's a really powerful combination to work together.
Raman spectroscopy as an analytical technique has become extremely popular over the last decade or so, now that small portable devices are practical. It's used for measuring pharmaceuticals, it's used in security applications, and it can be used in forensic crime scene analysis as well. For Mars, it's going to be the first time an instrument like this has ever been deployed, and it's particularly important because it's sensitive to the molecular composition of materials. It's a non-destructive technique, so you can operate it multiple times without damaging the materials that you're interested in looking at, and it simply uses a laser to illuminate the surface of the sample, and you collect the light that comes back off it, and by looking at the fingerprint that's produced, you can identify the specific molecules that can give you information not just on the geology of the samples that you've got, but also on potential organic signatures as well.
Today we've been testing the ExoMars instruments, PanCam and the Raman spectrometer on this field site here, which is actually an old mine site. And this site has got a whole wide variety of different types of rocks and different types of minerals, which we can actually test our instruments on. So if we look at some of the rock types around here, for example, so this is a hydrothermal mineral vein that was deposited within a hydrothermal environment. And we have lots of different minerals in here, including calcite, which is this bright white one here, and also quartz, the slightly darker grey one. And these are minerals which are deposited in a hydrothermal system. And this is very important for Mars because hydrothermal environments have existed on Mars in the past. And we know from the same sorts of environments on Earth that these are inhabited by a wide variety of sort of extremophile microbial life. So exactly the kind of life that we're trying to look for with the ExoMars mission. Matt's imaging some rocks at the moment with the PanCam instrument system, and he's imaging a slightly different type of rock. This rock is called a shale. So this is a very fine-grained, clay-rich rock, which also formed in an environment which is very conducive to microbial life. So this is a very calm, sort of very aqueous environment, very water-rich. The sort of habitable environment on Mars that we want to be able to identify with the ExoMars instrumentation so we can look for signs of life within this geological rock record.
Coming to places like this enables us to have trial runs and to investigate different modes of operation, different types of acquisition processes, so that you can get the very best out of the instrument. It can be extremely tricky when the instruments you're trying to operate are so far away to understand how they're going to respond to the different types of material you find. So we're only going to have a few opportunities to get the information we want, and it's really important that it's right from the very beginning.
These field trips are really important, whether you're an engineer working on the actual instrumentation itself, or perhaps whether you're a geologist actually working on the data and interpreting the data sets that you get from these instruments. As a scientist, that's really important to know how much you can actually extrapolate and interpret something. The area that we're working at the moment is a really good geological analogue for the terrains that the ExoMars rover will explore, primarily because it's a type of sedimentary rock which has already been identified on Mars.
You can regard this basin in between as being analogous to a large meteorite impact crater on Mars, where the impact has excavated deep down and thrown these really ancient rocks up to the surface and gives us a chance of sampling into them that we wouldn't otherwise have.
You have so many different instruments and so many different people of different scientific expertise working on these missions. It's a really important thing to have this communication between all the different members of the mission.
With a camera going to Mars, one has to be particularly careful about temperature. At night, it gets down to minus 100 degrees centigrade, possibly even a minus 120. So you've got to test the instrument to make sure it's going to work over that wide temperature range. Also on the surface of Mars, because the atmosphere is relatively thin, there's a radiation environment which is higher than we have on the surface of the Earth and even higher than we have at the top of the atmosphere. Also, because the atmospheric pressure is low, it has to work in that environment as well. But probably the biggest challenge is temperature. That type of thermal flexing in our real optical bench going to Mars, that is certainly a challenge.
The ExoMars PanCam instrument has been under development now for a number of years, but it's not actually going to be a fully functioning prototype for a little while yet, because it's such a long development time. So in order to allow us to capture test data in the meantime, we've built this emulator system. So it's representative of the PanCam instrument, although not physically the same. So this is built with off-the-shelf commercial components, so standard off-the-shelf cameras and lenses. But we've also manufactured these filter wheels on the front, which give it the multispectral capabilities. So we have two wide-angle cameras mounted either end of the optical bench and a high-resolution camera mounted just off to one side. It's absolutely critical now that we understand exactly what the camera's capable of. We're reaching the point where it's going to be too late to make any changes, so we really have to refine all the last details now. So all these field tests are critical for learning, more often than not, what we've done wrong in the past and how to fix it before it gets too late.
I've been lucky enough to be in this fantastic laboratory for the last 32 years. We're leading in planetary exploration, but also in astrophysics, solar physics, space plasma physics. So we have some fantastic work going on here. The unique thing about this laboratory is that we have scientists and engineers working very closely together.
Here we have a CAD model of the rover itself. This gives us an idea of where we sit within the system, so we can have a look at fields of view and things for our cameras and make sure that nothing's obscured. The 3D printed model is a selective laser sintered representation of the optical bench. The 3D print is very useful for us because we can produce something full size and we can actually start getting a feel for how the system will go together, how we can handle it, wire it up. A lot of hands-on work. We had this produced with all the subsystems in less than a week.
So what we've just been doing here is really exciting. It's machining for the PanCam optical bench, the engineering model of it. So this is one of the models which gets delivered to the European Space Agency. So the project has really reached a very exciting phase. So what we're using here is a state-of-the-art numerically controlled machine, which is really the top in its class. But there are other machines here as well, which you would find in any mechanical workshop in different places, much more traditional types of lathes and milling machines. So these are the types of things which are used for the work that we do, not only in planetary science, but also in space plasma physics, solar physics and astrophysics. So it's a very exciting state-of-the-art mechanical workshop.
The filter wheel has just finished its environmental test. We've been testing the filter wheel at the Martian environmental temperatures, minus 120 to plus 80 degrees C. And the test is now complete, and I'm just here to take it up to the integration lab to do some tests. Here we have an example of a filter wheel that we have been using in some of our testing. These filters have different colors, which means they're sensitive to different wavelengths.
For me personally, I've been trying to get something onto the surface of Mars since 1999, when we started working on Beagle. So now this is the opportunity, and sort of building really on that experience and building the team to actually send what is the best scientific camera to Mars. It's a fantastic opportunity. The science of this mission is going to be really fantastic. There are some engineering constraints on landing on Mars, which means you have to be fairly equatorial.
Equatorial, of course, because we're a solar-powered mission, and around the equator you have more of the sunshine more of the time during the year, so you want to make sure you can stay powered up for most of the time.
And we can't wait really to get it to the surface and to be able to have the rover roving around looking for sites to drill. PanCam will be playing a central role in the selection of exactly where to drill, so it will be able to do that with wide-angle cameras. And then combining that with a high-resolution camera, that will be a fantastic opportunity for geology and also atmospheric science.
Indeed, and from these stereo cameras we'll get good digital terrain models, that is, really details of the topography around us.
In terms of the big picture, finding life on Mars would be one of the most fantastic discoveries of the next decade.
The process of choosing a landing site is actually a balance between deciding on the main science objectives and trying to figure out which areas are the safest to land, and that involves usually doing a lot of scientific assessment using orbital data that we've acquired since the Viking landers in the 70s really, and also considering the engineering constraints, so making sure the surface is not too rough, making sure that the ground is not too soft that the rover won't be able to drive anywhere, things like that. So it's really a trade-off between the two.
One of the things that was a real challenge when we were told about the ExoMars landing site process was actually how little of the surface we get to choose from. And that's because certain areas of higher ground are ruled out. We're not allowed to go too far north, not allowed to go too far south. So actually it was quite a challenge to find a scientifically compelling place to go within these constraints. So just to demonstrate what I mean, this is a map of the central part of Mars around here. When you turn on what we call the filters, you can see these black areas. These are the areas that are all ruled out. So actually there's not really many places left to go. And we don't really want to go into anywhere around here because this is the remnants of an enormous flood. All that stuff is too young and we're not interested. We want to look at the few patches of really old stuff around this area.
And interestingly enough, the remaining area that was left after making all these constraints is about the size of Western Europe. It was a very small fraction of Mars's surface. So it really didn't give us that much to work with on such a short time scale.
Well, especially because actually trying to fit what's called the landing ellipse, which is an ellipse that designates the uncertainty for a given point where we would land. It's about 100 kilometers long. It's actually quite hard to fit a 100-kilometer ellipse into a space, maybe like this. If you're selected, the stress begins because eventually you'll be responsible or partly responsible for the choice of a landing site that a €1 billion mission will go to. And if you've led the landing site selection process for a specific site and the rover gets there and it shows things that are not what you said were going to be there, then, or maybe it hits a bunch of rocks that Elliot said weren't going to be there, then that's also pretty stressful.
But maybe you'll hit the jackpot and it'll discover
Absolutely.
Ancient life markers.
Yeah, it's good stress though, I hope.
What I've got here is a sample that I found yesterday when we were exploring. And this might not look like much, but this is a really exciting, very interesting little piece of rock. This is a piece of quartz. And when you pick it up and turn it over, you see the underside of this rock is absolutely encrusted with this green, which is cyanobacteria. These are simple bacterial forms of life that grow by the energy of sunlight. And what the cyanobacteria are doing here is using that piece of quartz in the very, very dry desert soil to provide microhabitat that is much, much more clement for living in than the desert as a whole. Because you can concentrate a little bit of moisture underneath the quartz here. But more importantly, the quartz, which is quite a translucent rock, allows just enough sunshine to shine through it that the green cyanobacteria can still grow by that light, but the quartz blocks the ultraviolet radiation. So it's almost as if the cyanobacteria are using this mineral as a kind of natural sunscreen, as an ultraviolet shield to protect themselves from this really harsh desert environment to survive in it. I'm really looking forward to getting this back to the UK, back into the labs, where I can use Raman spectroscopy and infrared spectroscopy and a whole bunch of other instrumentation and bits of kit to study this cyanobacteria, to study the signs that this rock has been colonized, that it's got life on it, and therefore hopefully trying to understand how we might be able to find similar signs of life on Mars. This is a really neat little piece of rock here.
It really is difficult. First, starting off with landing on Mars, just getting to the surface is difficult. Once you're on the surface safely, you've got to have something which will survive the extreme temperatures at night. That's why we do all the testing in the thermal chambers and so on, to be able to test for that. But once we have the rover on there, this will be a bit like a roving geologist, able to go around, look at places, decide the next target for the next day, and then drill underneath the surface. And that's the key new thing for the ExoMars rover, to be able to do that.
These rovers you see in the background here are effectively research and development platforms. They have some of the sensors we would expect to see on the real vehicle, and they allow us to test out some of the software that we have that is effectively implementing some of these autonomous systems ideas that we've got. And it allows us to test them out in the first instance in this quarry environment, which is kind of preparatory work for a later mission to somewhere which is more geologically representative, like the Atacama Desert in Chile, for example. Because Mars is so far away and we can't talk to the rover directly, it's a bit like we have to prepare instructions in advance based on a small amount of information. So it's almost like the rover sends us a little postcard, the guys try and work something out, they send some information back, it moves a little and it sends back another postcard. That's a traditional way of doing things, which is quite slow, but the rover, of course, has access to all the information right in front of it because it's there. So what it can do is effectively say, okay, you've asked me to go from A to B. I can build maps in 3D of the world around me. I can also work out where I am with respect to those maps. So even though you've told me to go from A to B in a straight line, I might see there's a big rock in the way. It can work out how to navigate around that rock and make sure that it reaches that target because it has access to information that the guys on the ground don't have necessarily when they're doing the planning. Mars does present some unique challenges, so usually what comes out of these kind of experiments is a really interesting fusion of ideas. So we have some technologies that were originally planned for applications on Earth. We have a unique set of problems on Mars, and we end up with a new technology usually which has reached beyond Mars itself and can be commercially exploited. So it's very much a circular kind of dependency. For example, you may want vehicles in remote parts of the world to do exploration, and you want to minimize the amount of energy use. You may have a remote platform which is surveying a distant oil pipeline in the desert. The vehicle, using the kind of technologies we've developed here, could indeed do the same kind of thing in those remote regions. It could also look out for targets on the side of those oil pipelines, maybe cracks, for example. We do similar sort of things in another way on Mars where we're looking for targets of interest from a geology point of view. So there's these really interesting different types of applications which at an abstract sense are effectively the same thing.
This is the Airbus Defence and Space Mars Yard in Stevenage. This is designed for testing two things. Firstly, it's designed for testing out the locomotion system of the rover. That's the wheels, the bogies, the motors and the sensors on the locomotion system. Secondly, it's designed for testing out the autonomy systems on the rover. That's why we've got quite a big room here. Essentially, we need to be able to put the rover at one end and say, find your way to the other end, and that allows us to test all the systems. Mars is a very long way away. It can be up to a 20-minute delay on radio signals getting to Mars. We simply don't have enough energy on the rover for it to transmit a signal back to Earth directly. So we have to talk via an orbiter that's going around Mars. Now that means we can only talk to it twice a day, perhaps in the morning and in the evening. All the rest of the time, in the middle of the day, it's all on its own. So we're developing the algorithms that allow it to control itself during the day and achieve the science objectives that we want it to achieve. The rover that we have here doesn't look exactly like the final flight rover will look. That's because Mars has a third of the gravity of Earth. So the 300-kilogram rover that we're going to put on Mars, this one has to be only 100 kilograms, so it has the same ground pressure on Earth when we're testing it here. If we look at the rover from approximately here down, it's a relatively representative rover. All of the bits up here are just designed to be as light as possible so we can keep under that 100 kilograms limit.
The rover structure development has taken quite some time. You have to go through a concept design and then you look into developing that and exactly how is that all going to be built, what materials, how is it all going to fit together. And then you develop some materials testing. So we've done that now and we're continuing to do some more of that. So to make sure that things behave how you'd expect at the low temperatures or after all of the thermal cycling, under radiation, all of those kind of things. Then you build and build and build and gradually narrow towards that final design. We're getting to the point in the build now where we're actually getting flight hardware in. We're beginning to see things going together in our clean rooms. The clean room's all ready for everything to be built for the final flight piece of hardware, and it's really getting to an exciting point, but it also means that everything's very real. All of the responsibility suddenly feels like it really is there, and you really do have to design something that's going to Mars. You're never going to be able to go and touch again, so it absolutely has to work first time. So that's getting quite nerve-wracking as well.
I'm back from Atacama now. I had a suitcase full of rocks to bring back through customs of geological samples. And I brought them here to the Open University, where I'm doing a lot of the analysis on the microscopic Raman spectrometer they've got here. I've got one of the samples here that I brought back from the Atacama. This is one of the pieces of quartz that you saw me sampling and picking up. And this is where, if you turn it over and look underneath, this is where you see the green colour, the colonisation of the cyanobacteria on the underside of the quartz, where they've been protected from the dry and the ultraviolet radiation in the desert. So we've put our quartz sample on the sample stage of this microscopic Raman system here. And what Raman does is it shines a laser beam onto the sample, and that light bounces around, interacts with all the molecules inside the target. So the light you collect contains information about the kind of molecules that are inside the sample. And when you look at the spectrum on the screen, you get a spectrum like this coming out. And these spikes in the Raman spectrum are the fingerprints of that quartz. This is how you identify the kind of rock that you're looking at. And particularly this very intense peak, about 464 Raman shifts. But if instead we target some of that green colour, this is the microscope view that we're looking at right now of the underside of that quartz rock, showing a clump of green. This is a colonisation patch of the cyanobacteria. And if we turn off that microscope view and put it to the laser beam for the Raman spectroscopy, instead of seeing the spectrum of the quartz rock, we see the spectrum of the cyanobacteria themselves, and particularly this triplet of peaks. This is the fingerprint, this is the spectral signature of carotenoids inside the cyanobacteria. So these are some of the compounds that those cells are using to help protect them from the ultraviolet radiation in the desert. So Raman is very good at giving you not only the minerals and the rock that you're looking at, but also the signatures of life itself clinging into on the underneath of those rocks.
meeting that we're here at today is a really good opportunity for us all to kind of just get together and present all of our latest research and kind of see where we can feed back into each other's work. So that includes people working on the instrument teams on ExoMars, for example, as well as all the scientists kind of doing all the background science as well, feeds into this mission.
Most interesting with all of these meetings, it's not what we've most recently learned, but what we've still got to try and work out. So every talk will finish with a conclusion slide and then a kind of questions that we've just realised we don't know the answer to yet.
There's a huge range of people who've come into planetary science. There's some traditional planetary scientists, there's geochemists, there's people like me who've entered the field completely new. The beauty of Aurora is it brings different groups together, and so you learn about other fields and how they can interact with other fields, and that's fantastic. What's exciting is that we've got a whole set of new young people who will actually be doing the hard work on these missions. They have the technical skills, the computational skills that these missions need, the engineering skills to really make this happen. So it's really a great meeting place for all these different groups to tackle these great science problems, actually one of the most fundamental problems we have in science today.
It does bring home a certain reality in the sense that you get a much bigger picture. It's very easy when you're just working on your own particular line of research to kind of get very focused on one particular thing. So yeah, when you get to see everybody else and see all the talks that people are presenting, it just it gives a really nice sense of the big picture of the whole endeavour.
It's getting very exciting because, of course, we're close to the first mission of a European landed rover on the surface of Mars as part of an international effort that's now been going on for decades to understand the past history and habitability of that planet.
Ultimately, I think we will soon be able to answer that question. Was there, and possibly is there even, life on Mars?
Sometimes I find it incredible that I'm actually working on active space missions. The fact that the work I'm doing at the moment is, in even just a small way, contributing to the ongoing endeavour of searching for life on Mars and just exploring the environments that exist just within our own solar system, let alone elsewhere. I find it very fulfilling to be part of this whole story. When we look at the planet Earth and we look at everything around us, we can see an abundance of biology and life. And the Earth is incredibly unique in this manner. We don't see anything like this anywhere else in the solar system. Through trying to understand the limits of life on Earth, we can try and apply this knowledge to really answer this question of whether or not there is life elsewhere. That's just a really exciting thing to be working on.